Welcome to the Henry AI Labs walkthrough of Keras Code Examples. Keras has provided 56 code examples implementing popular ideas in deep learning. This ranges from the basics such as simple MNIST and IMDb text classification, all the way to cutting-edge research ideas such as knowledge distillation, supervised contrastive learning, and transformers. We'll also explore fun, generative examples like variational autoencoders and CycleGAN. My contribution to these code examples is to explain every single line of code in each of them, walking through each of the individual Keras examples. I'm not the author of these code examples. Please consider starring the GitHub repositories to show support to the original authors. This Keras example will show you how to build an optical character recognition model using convolutional neural networks, recurrent neural networks, and the connectionist temporal classification loss. This is how you read a Captcha, like this collection of letters and numbers, reading it left to right, using deep neural networks. So this is going to be a really exciting application and really interesting code, particularly this CTC layer and implementing this custom loss function. This is definitely a different loss than you usually see with, say, categorical cross entropy or regression loss. The CTC loss has a bit more structure with respect to trying to decode the output of the model and align it with this left to right decoding of these images. In the Keras code example, we're going to abstract away this connectionist temporal classification loss by just calling it on the Keras backend. But here's a quick sense of it if you're curious about it and want to learn more about it. So I'm going to give a quick high-level overview of this. If you want to learn more, here's a great Towards Data Science blog post, an intuitive explanation of this that goes into it in more detail. But the important thing to know about this is that it's a way of decoding the output of a deep neural network. So if you've played with things like language models or the sequence-to-sequence text generation models, like maybe abstractive summarization or chatbots, or maybe even with image data and video data with different ways of decoding forward trajectories and say model-based reinforcement learning or predicting a series of videos, that'll be actually the next Keras code example, is predicting the next frame in a video sequence. So how do you decode these outputs? Because there's many different ways to sample along trajectories with respect to what the model is predicting. So this is one way of doing this as we're going left to right and reading a Captcha and decoding this into something like JERR, Jacob, or whatever, something like this, and we're decoding the output of our model. So the first thing to do is we process it with the CNN, split it into the features that have been extracted by the CNN, and pass it into the RNN, and then the recurrent neural network is going to make several different potential decodings of a prediction of the future and doing a left-right modeling of the potential words, which is HERR, Jacob, rather than the J that I originally said. But so here's the idea, the high-level idea of how CTC works. So we have these different paths along which at T0 the recurrent network is predicting, say, A with this density, or it would probably be better to find an example with different densities, or we'll look at this and pretend that the coloring is the density. So at each step, it puts a different density on each token. So see how at T2, A is a darker blue. Let's pretend that light blue means high, or you don't have to pretend, it's right here, color-coded. Light blue means that it's putting a lot of probability on that alpha or that alphabet decoding or number decoding, and then low dark color means it's putting no probability at that time step. So as the recurrent neural network is processing the patches extracted from the CNN left to right, it's putting different densities on the predictions of the characters. So we need to have a way of traversing this graph to sample several different potential decodings because it could be pretty noisy with respect to just doing the pure output from the RNN. So this is a way of doing an alignment of the potential ways of decoding what the RNN is outputting in each time step as it passes in the CNN extracted feature patches and then renders a final prediction for the Captcha. But again, in this Keras code example, we're going to abstract this loss completely by just calling Keras a backend.ctc loss. But if you do want to learn more about it, it is a pretty intense topic. Here is a deeper blog post. So finally, one last thing before we dive deeper into it and to get a quick high-level overview of what you're going to learn by going through this, I really like how this shows you how you can implement a custom loss and put it as a part of the model. So what that means is instead of having model.compile and model.fit to pass in a loss function, we'll see in this tutorial how the loss function is actually a part of the model. So we see how we have self.loss function, then at the end of these inputs we have loss equals self.loss, self.add loss, and then return the Y prediction. So we're adding this loss to the model, and what that does by having output equals this loss layer is it makes calling model.fit a much easier syntax compared to implementing a custom model.fit with this custom loss function. So this is a really common practice, especially when you look through advanced deep learning research code, is to see these loss functions integrated in the models to facilitate this integration of something that's much different from, say, categorical cross entropy or regression losses, to integrate this within the loop of having a layer that has loss function and then build model, and then in the end, when it returns the output, so when it has output equals CTC layer, labels X, meaning labels, so you also have to pass in the labels to the Keras input layer because the loss function is a part of the model. So we'll get deeper into this as we go through this code. So in the beginning of the code, we have the basic imports, a path library, collections, counter. These are implemented data structures in Python, the collections library, TensorFlow, Keras layers. This is the link to get the dataset of Captcha images. Once you download it, you can click the folder icon on Google Colab, and you can see the Captcha images. And if you want to, it's going to take a second to load the folder because there's so many of them. And then you can just click it if you want to get an example of what this looks like. So we have this data set. It says here we have a total. It's the data. That's the data is in like megabits. So I'm not sure exactly how many of these images we have, but it's probably safe to say maybe we can. No, so we have a few of these images. It doesn't matter. Oh, it says right here. So we have 1,000 of these Captcha images contained in this folder, Captcha images v2, that are downloaded by doing this link, whether you do the shell command curl, and then you unzip the zip file. This is the zip file. You compress the file so you can have faster data transfer across the web. So now that we have these Captcha files, we're going to need to parse them to get the labels from the namings of the files in the folder. So this is referencing how our data is labeled. The data is labeled by the namings of the images. So 226MD are the ground truth labels of the characters in the Captcha. Same with 23MDG, 23N88, and so on for all of the different Captcha images. So what this code is doing is first it has the data directory, this folder, and these files in the folder. This is the path. You traverse to this folder and then loop through these file paths. We have the images, we sort this to get the file path names, and then we have the labels. So what you do with this is if you have a string, this images is not actually images, it's the names of the files. So then we're splitting it by .png, so we remove .png, so all that's left is 226MD in our string, and then we're going to loop through the characters in each of the strings. So it says images, but really means the string of the file path. So we have the file path string, then we split it to remove the .png, and then we're going to loop through the characters, and we're going to count up how many file paths we found, how many labels we found overall, same thing, same idea, and then we're going to see how it's the same value down here, and then we're going to loop through and count the number of unique characters we see. So in this case, what's interesting is we don't see, say, I think it would be all 36 for 26 letters and 10 numbers. That would be possible in a data set. In this case, we only have a coverage of 19 of the letters and numbers in our encoding of these characters when we're going to parse this and turn this into the ground truth Y labels for this decoding task. So then we pass in the batch size. We're going to be passing in 16 images per batch, the image width and height. So kind of interestingly, we don't have a perfect square image, which is kind of common in computer vision, like CFAR10, ImageNet, STL10, and so on, is to have a perfect, say, 32 by 32, 96 by 96 image. In this case, we have a longer width and height, which is, obvious if you look at the image itself. This is you pass in the downsampling factor for the convolutional blocks. This is a hyperparameter on how the stride lengths and the pooling are going to downsample the intermediate sizes of the feature map. So this is not important for right now as we're pre-processing the data. Then what's important is understanding this max length of the labels. So we want to have a constant length of the labels. We don't want to have variable length labels, or even if we do, we still would like to have a sense of the maximum length. So it's possible that you can have a left to right decoding with variable length, but it's probably easier to either zero pad or something like that so that you have a constant size for the ground truth labels Y. So now we're going to pre-process the data, and the first thing to do is to do a character to number mapping. This is the common thing that you use in natural language processing to, say, convert tokens into integer indices. In this case, we're converting characters to numbers, and in this case we only have 19 characters in our data set, and we're going to convert this into 19 numbers. And then we're also going to similarly have a reverse decoder to go from the numbers back to the characters for when we, say, want to look at the output of the model and run inference. The next thing to do is to implement a custom data splitting function. We're not using one of these built-in datasets like TensorFlow.datasets or TFDS.load, and we're not using, say, the Kaggle competitions API, Kaggle datasets, or anything like that that's already done our train test split. We're loading data purely from these file paths that have been uploaded into our running time, and we have these pure file paths that we're using to load data. So what we do to define our own custom train validation splits is we have the train size, which is 90%. we multiply that by the size, and then make sure it's an integer. Then we split our array of file paths by using colon up to this number. So say it's 100 samples, would be up to 90 if we're doing 90%, 90, and then the remaining 90, and so on for the validation set where it's the last 90 for the x's and the y's. So now we actually call that function, and now we have these arrays of the file paths to load in the images. So now we're using the function that actually loads in the images. So what this does is first we call the tensorflow.io.read file where we pass in an image path like 245y5.png, and then it uses tf.io.decode.png. These are PNG files, and now it converts it to a grayscale image. So grayscale image just means that there's only one axis of this pixel grid, so it's just say like MNIST digits are 28 by 28 by 1 rather than RGB, which would be 28 by 28 by 3. So we're having these grayscale Captchas, which makes sense for Captchas. No need to have color with Captcha. Then we convert the image data type to float32, resize it to that 200 by 50 thing, and then we transpose it so it's compatible with the input to our model with respect to the time dimension, because we're going to be chunking this and having a special way of permuting this where we're going left to right along the width. Because we're doing Captcha decoding, we want our model to process this by going left to right and saying 2, 3, 5, 6, G, rather than just kind of looking at the image entirely at once. So this is a prior that we're cooking into this model to tell it about how to read this, and telling it that a left to right reading, which we're doing by permuting the order of this, just says we're pre-processing the data, is going to be an easy prior on how to decode Captchas. So now we use these functions and our file paths stored in xtrain and ytrain as well as xvalid and yvalid to pass this into a tf.data.dataset object. So first we use the from tensor slices to pass in our file paths. Then we call .map where we pass in our function that encodes a single sample, returns the image as well as the label in this way of processing this tf.data object. And then we pass this in, so now we basically have our images and our labels properly processed. We have the character to numeric, so we have the number labels of the file path labelings, which is things like 226MD and so on. And then this is how we get our data set. So next we call this matplotlib function to construct a grid of visualizing the Captchas as well as their labels. And now we're getting into the really interesting thing, which is defining this model and putting the loss function as a part of the model itself. So unless you're particularly working with a problem that has this left to right decoding and you're interested in the CTC loss and the particular details of this prior knowledge on the left to right decoding, here's what I think is the interesting takeaway for generally improving your Keras programming skills. What they do with this is they're going to implement this custom loss function as a layer. So first we have class CTC for connectionist temporal classification loss layer that inherits the Keras layers.layer. So what we're going to do is we're implementing this loss function by calling keras.backend.ctc batch cost. So batch cost, I wouldn't really be too worried about the details of this, but this is for the training set, so it's implemented differently. So another example of this is say with SimCLR and these contrastive learning frameworks, you need to have a different loss for batches. So just one way of thinking about how they're actually implementing this with respect to when you have these large matrices that are passed in. Because you don't do single example updates, you pass in batches, but again, don't worry about that for now. So self.loss function equals keras.backend.ctc batch cost. Then we call the function by, this is just processing our batch length and reshaping it for input to this, so because we have this batch. So again, I wouldn't worry about too much of this, but other than just seeing how this is just reshaping the data so it's compatible with this CTC batch cost. And then we're just using the yTrue, yPrediction, and then input length, label length, and then we're adding this loss function. So in this case, our call, our yTrue, yPred, this is going to be the custom loss function that we're implementing within our model. We now have a custom Keras layers that implements our loss function. So we pass in the inputs of the image and the labels to our Keras input layer, process the input image by passing it in with this Keras sequential API. Note how we're just passing input image to each sequential function process like a convolutional layer or max pooling, and not the labels call. So then we keep propagating the features X and so on with the functional API, as we see that propagated down. And then in the end, we use our loss. But maybe before that, we'll quickly go over what happens with this. So first we process the input of the width by height image. We've reshaped it to be width first, then height, in order to bias it with this left to right kind of syntax. And the reason that we do that, again, sorry if this hasn't been completely clear, but when we're doing this reshaping the transpose, we're moving the width to be in front, so it's not height by width, it's width by height. and that way it has this left to right for when we're passing it into the second half of the model, which is the recurrent neural network. So we first chunk it up and featureize it a bit with the convolutional neural networks, which slide these 3x3 kernels across the window. Say you have 5 layers of that, you have a little bit of global feature aggregation, but not too much. It's still heavily biased in local regions, and now it's doing a left to right decoding of the recurrent neural network that does things like time step 0, time step 1, time step 2. We've just replaced that with going left to right and chunking it as if it's time steps going left to right. So the leftmost part of the image is T0, rightmost part of the image is, say, Tn, T10, however big the image is, however big these chunks are, the step sizes that have been constructed by the convolutional features. So we're passing in convolutional feature maps, not the raw image. So the recurrent neural network is going to go left to right and right to left because it is an LSTM. It's not just a recurrent neural network, it's a bidirectional LSTM, but I wouldn't be too worried about that. All that's really interesting is that it's processing it and constructing these features of going left to right and also right to left traversals of the image and passing these features into a dense layer. And the dense layer is doing the decoding, where the dense layer has these outputs in this matrix, and it's going to be the outputs in this matrix are decoded with the, for our sake, black box. And again, if you want to learn more about this, here's a great article about exactly what's happening with this layer, but I don't think it's, I don't feel like diving in too much for this tutorial, for this quick kind of just trying to learn more about Keras tutorial. But if you want to learn more about it, the CTC loss is an interesting way of decoding these outputs. So then we have the model where we pass in the inputs as the image and the label because we're defining the loss within the model. And then we have the optimizer, we compile it and we return the model. And then you can see how many parameters it has. You see the output as you pass in these 50 feature planes into the recurrent neural network. I think it might be useful to get a better sense of the model to slowly walk through the model.summary. So we start off with the grayscale images. This is why this channel axis is 1. We've reshaped it in our pre-processing to be width by height, so it's 200 by 50. First, we apply a convolution with no spatial downsampling, so we have 32 feature planes, each with the original size, spatial downsampling with max pooling, and then another add more feature planes to the convolution layer, and then so on until we get to the final output of max pooling. So now what we do is we reshape these features. So we have 50 on our width axis, and we're going to smash the 12 and 64 together, 768, as we reshape this, and now we pass in these 50 by 768, 50 being the this width dimension, into the dense fully connected layer. So this is fully connected. This is a massive matrix multiplication with 49,000 parameters, and then we get our dropout, and now we pass in these feature planes to our recurrent neural network. So the recurrent neural network is going to walk along these 50 feature planes left to right and right to left, or 64 feature planes left to right and right to left. So the reason this one has 256 isn't because of this previous dimension. These 50s are what are aligned with each other. This 256 comes from this parameter on the model, 128 times 2 is 256 because it's going left to right and right to left. That's how a bidirectional model works. And 64 times 2 is 128 and so on. But this 50 is what needs to match to do this matrix multiplication. So we traverse the 50 by 64 going left to right from our previous layer and right to left, aggregating the features, and then we construct these recurrently constructed features into a dense layer, and now we have this 50 by 20 matrix. And as mentioned down here, this matrix looks something like this, where we have say 50, 20, and now we're going to decode this matrix with our probability densities along the 20, because 20 is our output space. We have 19 unique characters. I think maybe we've added another one for buffer sake, but so we have 20 characters to decode from. So 20 is this dimension and 50 is this dimension. So now we're going to be decoding this using the CTC loss, and something like that. Exactly how this works, I think, is not necessary for just understanding the basics of how this works. So we use this to decode the output of our dense layer and construct some loss to propagate back up through the rest of the parameters of the model. So now that we've defined the model, we put in the number of epochs, early stop and callback, and then we just call model.fit. We see the loss decreasing monotonically, or not completely monotonically, it goes up at this step. We see the loss decreasing over time as well as the validation loss, and eventually it converges to a very small loss value of less than 0.02, and the validation loss has gone down as well. So now we're going to look at how you can do inference with an individual CAPTCHA image. We've trained a CAPTCHA optical character recognition reading model, and now we want to decode it so that, or deconstruct it so that we can do inference with a single image rather than passing in large batches that have been designed for training. So first we index our model by doing model.getLayerName, and we get the image input because we no longer need the labels input, and then we get the output layer, which is this dense2 output as we looked at the model.summary. So we want this output in the model as we're now passing this into our inference CTC. So now we have our decode function, and this is where we're going to use the Keras.backend CTC decode, and we're passing in just one image to do compared to the batch. So we pass in the input length of the how many left to right characters it's supposed to be decoding, as we previously had looked up the max length of any one labeling as we had traversed through these labels on the Captcha images. And so it's using this code in order to take a single image and then left to right decode it, number to character. It's going back into the characters so that we can read it from the numeric outputs of the model in the original character form. So now we do validation dataset.take. This is a syntax to kind of like iterate through a data loader, and we go through the individual images in the validation set, and we can see the predictions that were made. So we see in this case 2WX73, it's got this one right, it's got this one right, and it's probably hard. Probably can do all these completely correctly, as we saw with a very low validation loss. So overall, this is how you build a Captcha reading model. A lot of interesting lessons to learn in this tutorial. Particularly this CTC loss has a lot of complexity behind it in the back end of how we decode this, and there's probably a whole research area in itself, particularly looking at language modeling decoding is a hot area as well, and learning how to do this kind of decoding.